4.5 linearization and Newton's method. I'm going to start by just asking an algebra question. So if you were asked to find equation line, find equation line, with slope of 3 going through -1, 4. I think we'd all use the slope-intercept form. I know I would. So y equals mx plus b. My slope is 3, my x is -1, my y is 4. I can solve for b, and I get 7. So the equational line would be y equals 3x plus 7. Okay, so that's the best way of solving it. It's the most user-friendly equation because I can look at it and know the slope and the y-intercept. Okay, that's slope-intercept. If I wanted to, I could use the fact that change in y over the change in x is slope, and that's called point slope form. You can use this to find the equational line given the same information. So the slope is 3. We'll call this x1, y1. So my y1 is 4. So I have y minus 4 over x plus 1 equals 3. Solving for y, I'm going to multiply by x plus 1. So I get y equals 3x plus 7 using the point slope form. So this is a thing, and we're going to use that point slope form to derive the linearization formula. So if I have y minus y1 over x minus x1 equals m, and I solve it for y, so then y minus y1 equals m times x minus x1. So y equals y sub 1 plus m x minus x sub 1. Okay, and if we write it in like a comma f of a form, we'll call this the linearization. That would be f of a. The slope, well, that's f prime of a times x minus a, and that is the linearization. So what we found is it's the equation of a line tangent to the curve at a point. Okay, so if you graphically, if this is my function right here, slippery little sucker, oh, and it rolled away. I'll grab a different one. A little humor to our presentation here. So if I wanted to find the linearization at that point right there, it is right there. It's the tangent line. Okay, so a lot of times we don't necessarily want to use our original equation. If we just want to look at just a tiny little interval, like from here to here, you can see that this green line is a pretty good representation of the function as long as the interval is quite small. Okay, so this right here, if we're going from here, from A to whatever that is, this point right here and this are the same because it's tangent. And now if I look at the original function, there's my new y value, there's my approximation. So that'd be my linearization at that point. So this might be a plus 0.1. Okay, so the linearization is not exact, but it's approximation for a curve in a given interval, but it's the tangent line. Alright, so on a test or a quiz, if you're asked to find the linearization and you forget the formula, you could literally just find the equation line tangent the curve at a point, and it's the same thing as this. But if I wanted to find using the linearization, let's say my example is find tangent line or linearization for f of x equals x squared plus 1 at x equals 3. Our linearization would be f of a, so x is 3, that's our a is 3, so it would be 10 plus our derivative f prime is 2x, so derivative at 3 would be 6. So there's our linearization, and we could clean it up and we get 6x minus 8. Okay, there's our tangent line at 3 for x squared plus 1. Alright, so we're going to segue into Newton's method. Linearization, if we made our L of x 0, so back to the green line, if I want to know what the x-intercept is, it's right there. Okay, and then we use this as our next L of x, and we get here. Now the red one has to continue. Now we use this as our next one, and we continue to use new L of x's and the x-intercepts of them. Eventually it'll converge to one point. Okay, and that's how we use Newton's method to solve equations that we haven't been able to solve before. So the process, if I make our L of x 0, that means we're going to find our x-intercepts. I'm going to distribute. Maybe it wouldn't make sense to distribute. Maybe I'll just subtract f of a. Move that guy over. So negative f of a equals f prime of a times x minus a. Divide by f prime of a. And add a. So I have x minus a equals f. Getting out of room here. So x equals a minus f of a over f prime of a. And that's Newton's method. I'll rewrite it over. Okay, so if we were going to solve like x cubed plus 1 or plus x minus 1, we want to find the zeros. If we want to solve x cubed plus x minus 1, what we need to do is find our initial approximate solution. So let's say we wanted to graph it. Kind of defeats the purpose of using Newton's method if we're going to use a calculator to graph it anyways. But I'm just going to save some time. Alright, so it looks like about 1. 1 would be a good place to start. So my first value is going to be 1. And I'm going to make a list over here. Okay, so my first value is 1. Now, to find my next one, I would use 1 minus f of 1 over f prime of 1, and that'll give us our next value. So it's 1 minus 1 cubed plus 1 minus 1 all over derivative 3x squared plus 1. 3 times 1 squared plus 1. So we get 1, 2, 1, 4. So 1 minus 1/4, 3/4. Okay, we have to keep doing this over and over again until we get the same answer twice in a row. But we can use our calculators, luckily. Like you don't have to do it all by hand every time. So what you can do is type in our Newton's formula, which is right here, and I'll use A minus, our f of A here is A cubed plus A minus 1 divided by f prime of A, which is 3A squared plus 1. Okay, so we can type that into our calculator, but before I do that, I'm going to store 1 in for A. Okay, you didn't see that. So I did 1 stored in for A. So now I know A is 1. So we're going to type A minus A cubed plus A minus 1 divided by 3A squared plus 1. Okay, so the calculator will do everything I did right up here, and they get 0.75. So 3/4 is what I got, 0.75. Okay, we have to do it again, but this 0.75 is my new A. So what I'm going to do now is store that in to A. Stores right down here. And I'd have to retype this whole thing. But rather than retype it, I can do second enter, and that brings me up, every time I do that, it brings me up a screen. So right here, or a line, I have my new line, which is what rather than retyping it, I can just pull that up again, and I get 0.686, yada yada, 0.686, and a whole bunch more. Okay, so we're going to store that. Second enter, do it again. Alright, so it looks like we're getting close, 0.682. Store that. Second enter. Okay, these two are still not quite the same. 0.6823. I should really write them all out. Now I have some room. I'm doing that. Okay, I'm going to store that. Second enter. 0.6823278,038. That might be the correct answer. Let me make sure. Yeah, we got the same thing. So 0.6823278,038 is the answer using Newton's method. If I graphed it and I calculated the 0, I got 0.6823278. So same answer using Newton's method. Alright, I have more from 4.5, but I'm running out of time here. My videos only can go 15 minutes. So I'm going to stop it and do some examples after this.